at axial loading and determine how deformation works when we just have axial loading. And we're going to start by looking at Saint-Venant's principle, which essentially states that very near the point of loading, you've got lots of distortion, very non-uniform stress and strain going on right around the point of loading. Far away from it, then you have nice uniform loading. Okay, so that's really what that principle states. Pretty straightforward. You just move away from the point of loading to get nice uniform deformation, stress-strain relationship. Okay, so most of what we do lies in that region where I have uniform deformation. So axial deformation. Let us look at a member. Okay, it's got changing cross-sectional area. It's got several forces on it. One force on the left end, one force on the right end, distributed force in the middle. Basically, my force changes as I move along the length. Okay, has a length. So I'm going to look at one little section of it right here. Okay, at some arbitrary distance x from the left side, it's going to have a thickness of dx. So that little member is right over here, and at that point I have a force. Okay, and that's a force specific to the x component, or because that load changes as I move in the x direction. So, but at this point, I have some p as a function of x. Okay, it has a thickness of dx. Okay, and then that force causes a change in length of d delta. Okay, so like an infinitesimal change in length. So my stress is force over area, and again, both the force and area are a function of x in this sort of a situation here. Okay. I also have my strain, which is the change in length over the original length of my infinitesimal. So it would be d delta over dx. Okay, and then you'll remember Hooke's law states that my stress equals the modulus of elasticity, or Young's modulus, which also could change as a function of x if I've got different materials or whatnot. Usually that's constant, for what we're looking at, but a lot of times it does actually change as a function of x times that strain. So using Hooke's law, plugging in stress, force over area, and strain, d delta dx, you can get an equation that looks like this. Now I'm going to solve this for the d delta, basically the change in the length. Okay, just by moving things around, you get that sort of thing. Then I integrate both sides, and I can find the total change of length by integrating over the entire length. So integrating from 0 to L, I have the force as a function of x times dx all over the area as a function of x, E as a function of x. Okay, so that is the full equation, the general equation of the change in length of an axial loaded member. Okay, we've talked a little bit about sign convention. If it's in tension, it's positive. If it's in compression, it's negative. Okay, so if it elongates, that's a positive. If it contracts, it's negative. Okay, which I believe we've talked about previously. Okay, now, the very common case where I have a constant load and a constant cross-section. Okay, typically we just have a constant cross-section, single material. That's why A and E are constant, can come out of my integral, which is, again, very constant, where we just have a straight cross-section, all made of steel or aluminum or something. And then if I just basically have loads at the endpoints, like in a truss or something, where I've just got a two-force member, then the P can come out of the integral, and all I'm left with is the integral of dx, which, again, is just going to be from 0 to L, so it's going to be L. So I get the change in length in this sort of a situation with a constant load, constant cross-section of PL over AE. Okay. Then if I want to find like the total change in length, let's say I have abrupt changes, say I've got a load at the midpoint, or I've got two pipes linked together. So there's a change in area, change in modulus. Basically, I can break it up into sections, find the change in length of each section, and then add those sections together. That's essentially what I have here. I just sum up all of the lengths, the change in lengths of the sections to find the total change in length. Okay, so again, this is how I can, from the loading, knowing in the cross-sectional area and the material and things, I can find the change in length due to an axial load.